Thank you. Thanks, Aninda. So I'm giving 6 lectures, right, Aninda?
Yes.
6. So okay. So I will please stop me at any time because it's not like I have to finish in any lecture some particular content. But let me give you like a rough roadmap of what we want to do. So the main source of motivation for us is to look at what we will call, and some of these words, if you are not familiar with right now, don't worry because I'm just introducing like the plan of lectures. But of course, as we go ahead, we will understand technically what some of these words mean. So the sort of the main motivation is to have further our understanding about gravitational scattering, by which we mean scattering of massive objects like black holes, neutron stars, which are interacting via gravitational interaction. And we can, of course, divide it into two parts in some sense. One is more fundamental, where you put h bar not equal to 0, and then you take the classical limit, and you get gravitational radiation. So of course, we know that from first principle, we know that gravitational radiation is something in principle you can compute using your equations of motion. So if you have general theory of relativity as a theory of gravity, then you use Einstein's equation. And if you have some objects colliding or scattering, then you can use equations of motion to compute the radiation. But in general, these things, I'm assuming that people have had one course in gravity, so please stop me even at this stage. These are not analytically possible to compute how much energy is coming out in a gravitational scattering. So the idea is to have, without going to computers, how much analytic hold we have on this object. That's one of the motivation. And of course, the deeper motivation is to understand what we call S-matrix in quantum field theory, and how much understanding we have about this S-matrix when we have gravitational interaction. And the basic, everyone knows, for example, here that ultraviolet, if you go to high energy, then gravitational theory is not renormalizable, so it's very complicated to understand quantum gravitational scattering. But what I will try to convince you is that even in the what we call the infrared, by which we mean that for example, the scales involved in the scattering, if two particles or two stars are scattering, the scale involved is very large compared to the radius of the size of the objects. Even in the infrared scale case, there is a lot of rich structure which goes under the name of quantum factorization theorems. When you turn on h bar, and they go under the name of what we will call event shapes in or what we can also say call low frequency gravitational radiation. So there is a lot of rich and interesting and a lot not understood structure, even if you are looking at low energy aspects of gravitational scattering. And the whole idea of these lectures is to understand, discuss, what we understand and what we don't understand on both sides of this diagram. So the rough plan of the yeah.
If you do this numerically,
yeah.
Are the results trustworthy?
Yeah. So we will discuss this. So if we look at whatever analytic formula we find, and if you, for example, try to match them with what people do during the in-spiral phase in post-Newtonian, they match fantastically well, but they match with a lot of caveats that we have to take into consideration. But yes, they are consistent with.
So the fault is with the numerics, or?
No, it's not a fault with the numerics. Yeah, I can say more. I mean, so here we are looking at scattering, whereas in the in-spiral we are looking at a bound state problem. So if you naively think that the scattering is more like a bound state problem with elliptical orbits, which is slowly decaying, whereas most of the post-Newtonian computations are in what we call quasi-circular or circular orbits, and there is qualitative difference when you go from almost circular orbit to a elliptic orbit. So in that sense, this result we find actually help us understand some parts in the post-Newtonian expansion. Yeah, and so roughly the plan of the lectures is that we will discuss what Okay, sorry, just one more thing I want to say. Why am I calling this some radiation? Why am I giving it a name? Because the reason I'm giving this a name is because these objects that we will compute in classical theory, they have analytic formula. So they are special, as we will see in some sense. Like we don't have to, we don't have to rely on exact all details of the equations of motion to compute some of these low frequency aspects of gravitational radiation. So whatever we can compute without knowledge of all the equations of motion, we will call it event shape, because as we will see, it's something special that we can just write down. Whose equation, formula for this we can directly write down for any theory of gravity. So the idea of the lectures is that for maybe first 2 or 3 lectures, we will focus on classical theory. And try to study low frequency radiation in classical scattering. And then we will, once we understand the structure a little bit properly, then we will look at the how there are similar structures with, of course, a lot more beautiful complications and richness when we go to the quantum S matrix. And everything gets tied together because of infinite dimensional symmetries that gravitational scattering obeys. So this is an entire subject in its own right, which is called asymptotic symmetries. These are symmetries which act far away from the sources which are scattering at infinity, and they really constrain both low frequency classical scattering and also the quantum S matrix in the infrared. So we start from our goal is to start from gravitational scattering and end with some understanding of symmetries of gravitational S matrix. So that's the rough plan. So please, if you have any questions, please. Yeah.
So far the motivation is concerned. So how much of this can actually enable us to differentiate Einstein's gravity from something else, say in real experiment, the existing ongoing experiments?
Yeah, that's a beautiful question. So as we will see that most of these event shapes, the reason they are interesting is because they are universal in the sense they are insensitive to the Lagrangian, in the sense that you start with Einstein-Hilbert, you add some higher derivative term, this formula for this will not change. And so we will see that there are some of them which do change, but we know in some sense the dependence on the theory. But their power lies in a orthogonal aspect to what you just said, in the sense they are insensitive to what the dynamics is. Yeah. Yes. Exactly. Yeah. Exactly. 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 Now, intuitively, yeah. 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 That's. Yeah. No, that's absolutely. That's really the correct physical way to understand it. The higher derivative terms do not change these event shapes, and that's any term that I think also Ananda had in mind, like Gauss-Bonnet type terms in higher dimension, will always have more derivatives than. Okay. So this is our setup. So our setup is the following. So let me draw a diagram first, and you should question this setup in the sense that I'm going to. Okay, let me explain the setup. So we have, astrophysical objects with incoming momenta, let's say P1 to Pn. So you can think of these as curved black holes, for example. I will try to explain why it is justified in thinking of black holes as point particles the way I'm drawing here. But for a moment, just bear with me. So think that you have some objects like black holes with some incoming momenta and some incoming spins, which I will just denote. So this sigma is the intrinsic spin of the object, as for example, you have a spinning neutron star. So if we should distinguish between the sigma and the orbital angular momentum of these quantities. And so these objects come from far out, from infinite distance. They collide, and then some scattering happens. So this is dependent on what theory we are looking at. We have Einstein theory, then something happens. We can have electromagnetic interactions if they have some charge, and some more complicated stuff can happen. And then this will go out into, two black holes can merge, or some things can fragment. You have some repulsive forces, for example, and it can go out into objects with momenta P1 prime sigma 1 prime to Pm prime sigma m prime, and I'm not keeping m and n same because we can have merger of black holes, right? So two black hole merge and give us one. So the number of incoming and outgoing objects is not the same, even in classical scattering, because we are allowing for processes like fusion. And so of course this will happen, and then radiation will be emitted. And so this radiation is some gravitational field that we measure at very large distance from, so for example, center of the scattering, and that is. So please ask if if the notation is not clear. So what we mean is that if I take the metric, then we can write at very far distance as the flat metric plus whatever else. And I don't mean that this is small. So this H notation should not lead you to think that I'm doing some expansion right now. This is just a way to write metric at very large distance in terms of the, we are just kind of doing, if you want, a random decomposition of any metric, which is solution to Einstein's equation in terms of flat metric and everything else. The reason we are interested in this way of writing G is because we know that far away from the source, metric is approximately flat. So that's the motivation for looking at this kind of artificial decomposition. Oh, yeah, or that was, but sorry, yeah, but right now it's, I will keep it, but it's a flat eta, thanks. But yeah, okay. And now the statement is that we want to look at this h mu nu at very large distance. So what I mean is that we want to consider, so let's take this x to be t and x in our Cartesian coordinates, and then if you study h mu nu, this is something we will see, then the expansion of h mu nu in distance goes as, okay, I call this 0. I will explain the notation. Okay, so let me explain what the notations are. So as we will see that when you try to solve for the metric at a very large distance in some coordinate system, you fix some coordinate system, and you are going at a very large distance from the coordinate system, you will see that typically all solutions die down for this h guy like this. So it has a, see, this x hat is simply will always be our notation for unit vector. So it will always be this. And if you are in d dimensions, we, of course, our object of interest is going to be 4 dimensions, but let me right now keep things more general for the purpose of this lecture. So in d dimension, one can check that the first term in h always falls off like this, and then you have yeah, d minus 2 in brackets, d minus 2 in brackets, yes, exactly. So so in odd dimensions, for example, there will be a fractional power at which your metric will fall off at large distance from the center of the scattering, but in even dimension, in 4 dimension, it goes as 1 by r, which you will be familiar with also in general from just studying gravitational waves. And so it is this quantity which is called the radiative metric. Radiative metric. So it's a function of time and the angle on the so let me put d here to indicate d dimension, sorry. And when we compute, or in LIGO, or in gravitational wave detectors, when people compute the flux emitted, for example, it's computed out of the energy momentum tensor that you build out of this object, this particular object. So it's this object which is of core importance when we study gravitational radiation. It's, you just study the leading order, you do a large mod x expansion and look at the leading order component of the metric. So yeah, so but right now we are, right, so that's why this is radiative. So right now I'm only looking at the radiative modes. Certainly there will be Coulombic modes, but that is not of interest for us for radiation. Yeah, and so so that's the object we want to understand, and for it's more convenient instead of working with time, because it's usually we are always interested in saying that okay, how much energy is emitted in the frequency window between some E and omega and omega plus delta omega. So it's more convenient to Fourier transform from time domain, and we can work with and now something interesting can happen, because we know that, so please ask at this point if these notations are not clear, that we can always write this t in terms of retarded time. So we can write it as, the retarded time coordinate is always defined as t minus r. So everyone is familiar with this. So that means that t is u plus r. And so this u is the, if a source emits gravitational wave at some time t equal to 0, then it's at some u that which will be given by the distance that the wave will reach at later time. So it's the u which is really the time coordinate at infinite distance where the detector is placed. So just for convenience, it's always we can rewrite this as so this quantity is of course h mu nu, and we put tilde for frequency transform, but this is of the form e to the minus I omega r integral du e to the minus I omega u h mu nu. The reason I am writing it in this trivially, I am rewriting this in this way, is to just make contact with the literature, because when you study gravitational radiation, you will always see that there is a phase like this hanging around e to the I omega r if you are measuring the, oh sorry, this r is mod x, I apologize. And so you should not be confused with what we are doing, because this factor is simply coming because you do Fourier transform in the retarded time, and so you will always have this extra factor. Okay, there. So this is really the object that we want to understand, and so we want to solve, we want to see how much hold we have on this object in a generic classical scattering. So that's our goal right now, is to just from the fact that theory has general covariance, and there may be something like total linear momentum of the system is conserved, total angular momentum of the system is conserved, using these properties, basic properties. How much can we say about how much hold we have on this object? Okay, that's the goal. Okay, so if there's no question about what we want to do, I will proceed. So please keep this setup in mind. This is our object, and now I will justify why it is okay to call, why I am treating black holes like point particles in a minute. But so that's even if you don't worry about black holes, you can just think that it's some scattering of point particles which have some intrinsic spin, even though they are classical, and then you are scattering them, and then studying the emitted radiation in d dimensions.
You're looking at this fall-off, but there could be fall-offs which are even stronger than this.
Means
in some d dimensions. In 4 dimensions, probably not.
no. So that is a generic result that in higher dimension, the radiative metric will always fall off. This
yeah, the radiative metric will fall off like
yes.
This, but there are other components of metric which might
Right, but they are not radiative in the sense that, okay, so I didn't want to say it right now, but when we say radiative metric, we mean that we look at only transversal modes.
Right.
So transversal modes, this is the slowest fall off. So there will be longitudinal modes, as he said, Coulombic modes, but they are not of interest to us as our detector is only going to be sensitive to the transversal modes.
Right, but sometimes Gauss law might relate the Coulombic mode to the radiative.
Sure, yeah, but but you're right, absolutely correct. But I'm saying that if you as soon as what we are interested in right now is to look at this metric, in a what we are interested in looking at the radiation coming out of scattering, as we will see, and the property of Green's function tell us that this, for the transversal mode, this is the fall off, like nothing more. Right? That's all we are using.
You might still be interested in some of the other modes.
Yeah, if you are interested in other modes, then of course it's more.
Interested just in radiation, we might be interested in them, right? Because they are.
So as we will discuss that, as far as event shapes are concerned, we do not need information about the Coulombic modes except in 4 dimensions. So I will come to that. Yeah, but right now, that you are absolutely correct. Everything you are saying is correct. But I'm saying that the object of interest is this, and of course there will be complications, conceptual and technical, to compute this thing. That. And what what you say is actually I would say a core of a difficulty in going from dimension larger than 4 to dimension equal to 4, where these things are.
Exactly the point that was made
But yeah.
is useful when you're looking at angular momentum radiated
Absolutely, and that is all built out of this. This is a basic object. So the not only energy flux or momentum flux, angular momentum flux also is always computed from this object. So everything is.
usually there is angular momentum is r cross t, so there's a power of r in the numerator.
That comes out of this. So the angular momentum will, the angular momentum of the field I am saying, that has some power of r, but it's built out of the stress tensor that we compute out of this. So, the object of interest is this, everything else is coming built out of this. So yeah, so that's a good point. So this is a metric, by the way. So this is not the energy or momentum, right? That is all built like in field theory, how we do from this field we build.
Maybe what I'm going to say is that if you look at the component of x which falls off faster than t minus 2 by 2,
Yes.
then wouldn't that contribute?
That will contribute exactly in 4 dimensions.
Exactly. Okay.
Yes, exactly, in 4 dimensions.
So
It does influence in 4 dimensions. Yeah. So because of what Sachin and Sid just mentioned, we are going to start by looking at these event shapes in d greater than 4 dimensions first. So our setup is this, and we want to look at radiation emitted in, so we want to study this in d greater than 4 dimensions. And as we will see that when we study this, you will see why d equal to 4 is complicated compared to d greater than 4. Many of you would know why, because of what Sachin and Sid mentioned, but if you don't know, don't worry. While studying the radiation in d greater than 4 dimension, we will see the difficulties we will encounter when d becomes 4. And that just comes out of the analysis of this, what we are about to do. But now let me give a justification of why it is okay to treat these objects like black holes as point particle, and how can we actually do it. So the intuitive reason is of course the following, that if we are interested in low frequency radiation, and we are looking at, of course, we are first of all measuring radiation at large distance from the scattering. So at large distance from the scattering, every object looks like a point particle plus some correction, right? That's just basic physics. Now, okay, but how do we quantify the intuition? If you give me a Schwarzschild black hole, which is say moving with some speed v, how do I quantify it in terms of a point particle? And that quantification comes as follows. So let me write a stress tensor first for a point particle with generic multiple. So we'll forget black holes or stars for a second, but we will say that we have point particles with complicated intrinsic structure, like not just not just linear momentum and spin, but it can have some other extra degrees of freedom, which I'm just calling multiple moments. And now I'm going to give an ansatz for the stress tensor of this particle, and then we will try to justify why, if you have particle with generic multiple moment, this is the correct stress tensor to look at. And part of this information came from work of Sid many years, 2016, right? 2016. So for a generic point particle like this, if you want to compute the stress tensor at any point x in space-time, so right now, sorry, I should also mention, right now for this part of the discussion, we are in Minkowski space. You may ask, this is of course ridiculous for our case because we are not in Minkowski, but you should think that when these black holes are coming from infinite, like early time, they are of course far out separated in space and they are moving with some velocity and colliding. So as farther away you go in time, they are farther and farther separated. So then each of them is in a Minkowski space-time approximately. That I hope that statement makes sense. But anyway, we will quantify it. But what we are doing now is stress tensor for a particle in Minkowski space-time, and that can be written in this form. So let me write and then argue why this is correct. So let's say that, yeah. So we are in d dimension, so I always put d. Oh, sorry. Okay, so I have written only first two terms, and now I will try to, I hope you realize that if you have just a point particle with no extra structure, then everyone would agree that if it's moving with a, on a curve which is parameterized with some affine parameter sigma, then we can rewrite the stress tensor of the particle in this form. So if, is this term, everyone is familiar with this term? Like you just have a point particle which is moving in flat space with some, along some trajectory r mu of sigma, and this is the, so of course, where p is the momentum and v is the velocity, and of course they depend on time because this may not be moving with uniform velocity or anything. So they, your acceleration is accounted for in this expression for the stress tensor, evaluated at some point x. So is everyone okay with this part? And now the point is that if the particle has intrinsic spin, like say curved black hole, then the first correction term one finds is of this form. And now I will try to argue why this is the case. So take, this is right now some ansatz. So what's the, you see, if you notice the structure, the main point is that your trajectory is not quite localized at, I mean, you are not only getting contribution when x is equal to r sigma, but there is a slight gradient that is involved in this expansion. So let me first try to argue why this is the correct, this is the correct term if you have spin, if the particle has spin, and this was derived by Sid and its collaborators many years back. And the basic reason is very simple, as they explained, that okay, let's just compute the angular momentum from the stress tensor. So we just compute. So say that again. Yeah, you are right actually. Why am I saying that? Yeah, maybe this term is already accounted for in standard textbooks, right? And the reason, okay, so but the reason that you are right, sorry, Weinberg already has it. And the simple reason is the following, that if I take this T mu nu and compute the angular momentum of the total angular momentum of the particle, so we do d cube x, x mu t 0 nu at some fixed time t and x, and with this, and then we see that this turns out to be equal to r cross p, r wedge p mu nu plus sigma mu nu. So you can verify this identity, and that basically tells you that okay, sigma, this is a correct, because sigma is supposed to be the intrinsic spin, so that's adding to the what we would call orbital angular momentum, and so then that's a correct term that we would add if we had an intrinsic spin for the particle. And now the point is that if you have more complicated multiple moments, then what we mean by that is simply that we have terms which go higher and higher order in these derivatives which act on delta function. So let me give one example of that term. And this is a remarkable structure in its own right. Oh, sorry. Okay. So the other terms are of the following form then. So these remaining terms, we go as some t mu nu alpha beta gamma do alpha or do alpha do beta Now you can say, okay, now I'm just telling you what it means for a particle to carry a multiple moment, arbitrary multiple moment. Do I have any data point which says that this is the correct way that, if I take a black hole like a curved black hole, do I have a data that if I look at curved black hole from a large distance, then it will look like a point particle which has a stress tensor which follows this expansion. Is the question clear what I'm saying? That and the answer is yes, and this was provided by Justin Wines in 2016. So Justin Wines showed the following. that if you take metric of the Kerr black hole, and I'm interested in looking at Kerr black hole from a large distance. So once again, I think, so has everyone at least heard of what a Kerr metric is? It's like Schwarzschild plus spin of the particle. But if you look at the metric of a Kerr black hole at large distance, it will look like plus some term, oh, this is in 4 dimensions, for example. His proof was in 4 dimensions, plus correction term, which, let me put 0 again. So this is simply a result of take your Kerr metric and do expansion in large R, just that's it, nothing else. So when you do it in 4 dimensions, you get a term which is flat metric and a correction term which goes 1 by R. And of course, this is related to Sid and Sachin's comment that Kerr metric itself has no radiation. So you may worry that why this power of R matches with the power of R here in 4 dimensions. But these modes, this metric is not transversal. It has no transversal components. So that one can just verify by looking at the form of this metric. And now it turns out you can ask, well, if I look at this metric, can it be sourced by a point particle? This metric is complicated in the sense it depends on the, so h mu nu Kerr, of course we can explicitly write, it's a kind of a messy metric. But it depends on what parameters? It depends on the mass of the object of the black hole and the spin, which is, let me call it sigma. These are the parameters on which this metric depends. Now, of course, it will only depend on mass if the object is only spinning and not moving. But if you boost it, then it will, instead of depending on mass, it will depend on the momentum. No, eta mu nu is a, oh, I apologize. Yeah, so if you boost it, if you boost it, then of course it will depend on the momentum of the moving black hole and of course the spin, whatever the spin of the Kerr black hole is, which is just a parameter in the metric of the Kerr black hole. It's just fixed parameter, it doesn't change, depend on time or anything here. And now this metric, you can ask, okay, is there any source which induces this metric, in the sense that if I solve linearized Einstein equation, so please ask if something is not, if you have not seen this terminology before. For example, box h mu nu equal to t mu nu. Is there any stress tensor of a point particle whose solution gives me this metric? So this was the question that Justin Wines asked in an absolutely remarkable paper, I feel. And where this box is, of course, the box of the eta, because we are doing everything around at a large distance where the background metric is eta, so maybe I should explicitly indicate this dependence on eta. And then he derived this, okay, because we know the form of this, it's quite a complicated form, but he could, he could find out, he gave an ansatz for t and then solved such that you get solution to this equation. And the t had the following form. So let me write t. I will erase this part. Maybe this one. So the t that he found had the following form, and I think Arka is the expert in this, so he can correct me if I write something wrong. So t has a form which was t mu nu of scalar particle, which is just this term, which depends only on the momentum of the scalar particle, so that will depend on p. And on that, we act with some, okay, I will write and then it will be clear what the notation is. Oh, no, it's, and then is it dou by dou p, Arka, or is it del by del p? Or, oh, no, it's not. It's this, sorry, because this, yeah, I will explain. Of course, it localized at point x, right, times. I explain this notation in a minute. So, this is some scalar product of some quantity. So sigma is a two form, sigma has two indices. So you take sigma alpha beta, p gamma, then you do epsilon. So this object I have written is, maybe I erase this part, sorry about my board work. So the exponent is epsilon mu nu alpha beta, sigma mu nu p alpha dot dou by dou x beta. Okay, that's the what is written in the top line, and this acts on integral d sigma delta d x minus r sigma v mu. So in general, of course, we are taking it with uniform velocity, so v and p are independent of sigma, but I'm just for generality writing it, I'm keeping dependence of sigma, although it's trivial in this case of Wines. So this derivative, of course, hits this. This derivative also, of course, hits this. Hits this quantity here, and now you do the expansion, and you see that first term, of course, is the scalar t, obviously. Second term will be the one that we just wrote down, this term, because, and you can see there will be one derivative hitting delta, and as you do the expansion, you have infinitely many derivatives that hit delta, and so this is an explicit example of taking an astrophysical object like a Kerr black hole and view it as a point particle this is a one concrete example of that type. And now you can ask, but here all the coefficient, what is remarkable is that if you do this expansion, all coefficient of all the derivatives, like first, second, third derivative, they're all fixed in terms of sigma and p. And this is what is in general relativity called no-hair theorem, that all the sort of objects of a Kerr black hole are fixed by only two parameters, like velocity and spin. And so this is a one manifestation of particle physics manifestation of no-hair theorem, which if there are some relativists in the audience, they would kill me because it's some complicated GR math theorem. Yes, thank you. So I think there is some discussion of finding a t at subleading order, but I don't know how far they succeeded. In this paper, they only did, is that correct, Aka? That only the one by atom.
So just to understand, this exponential, when it acts on this object, will literally reproduce the t mu for a scalar particle.
No. The first term, there's an exponent. So the first term is 1, so that is a scalar. Second term is when you have one derivative. So that will hit a delta. That will give you the term that we have for the spinning guy. The third term has two derivatives.
Then it's not the t mu of a scalar particle.
No, this is acting on the, so this is the t of Kerr. So the statement is the following, that the t that produces this h has this form, this is what Wines proved in 4 dimensions. Now this t, if you do expansion of this exponent, it is infinitely many terms, which all go as how we had written like this. So it's a concrete example of an astrophysical object which can be thought of as a point particle when viewed from large distances.
Because you are ignoring the gradients.
No, I'm keeping all gradients. So that's what I'm saying, that our answers were that for a point particle with arbitrary multiple movements, maybe it's a trivial statement. I mean, I thought because of students, I just wrote it that if you have a particle with a lot of internal structure, we can parameterize the stress tensor in terms of the scalar part, then a spin part, and whatever extra multiple moments the particle may have. And you could have asked, okay, do we know any example of some object whose stress tensor is like this? And actually, a very concrete example is Kerr black hole. So this, I don't know if I answered your question in that. So this is fitting into our classification of stress tensor of a.
I thought the way that you described it, you were trying to ask if that t mu on the right hand side of that equation, the linear Einstein equation, could arise from the t mu of a point particle.
Yes.
But
Yes.
Your answer is saying that the answer is no because there is this exponential dressing factor that is outside.
But it's still point particle with multiple, higher multiple moments, all of which are fixed by sigma and p.
So are you saying that?
So we look at this term, which is the term that I want to give an example where if you have a point particle with spin and some quadrupole moment, like what would the contribution of the quadrupole moment stress tensor look like? And the statement was that it would have this form. And this is one example where you explicitly see it, where the object is actually like something which we can relate to. I don't know if that. so then this coefficient will depend on, they will all be independent of each other in principle, right? If you have a complicated neutron star and you try to do this, then coefficient will depend on details of the neutron star, equation of state, etc., right? Not only on mass and spin, but in Kerr black hole, everything is fixed by mass and spin. So that's just, we expect that even if we write Kerr black hole as a point particle, and it has infinitely many contribution in terms of this gradient expansion, we expect that every term will be fixed only by two parameters from Noether theorem, but we now have a concrete verification of that statement.
Can I make a right question? So these are black holes, these are supposed to be classical objects.
Yes.
I would have thought that classical objects should be described by coherent states. But it seems like you just have one creation operator acting in the vacuum.
No, that's an excellent point. So right now we are doing only classical theory. When we try to understand, if you try to understand this as arising from quantum S matrix of point particle, then you would certainly write that as a coherent state. Right now I'm just ignoring any H bar correction. So coherent state is same as just a particle, a definite trajectory.
But strictly speaking, coherent state is not the same as a...
No, but that is if you switch on any H bar, you are absolutely correct. But right now I've just kept everything classical, not semi-classical. So I just ignored the coherent, the non-trivial part of the coherent state. But when we do, certainly when we do S matrix connection with quantum, we will do that.
So, whatever you say, right?
No, yeah.
What ADM? How would you, I mean, you can discuss ADM
Yes.
classically.
Yes.
So, if you have just only one Kerr black hole in the universe,
Yes.
then the mass is replaced by m times square root of 1
Yes.
minus v squared plus c squared.
Yes.
But if you want to do scattering of more than
Many Kerr black holes. Yes.
according to ADM, there is only one mass.
No. So no. So the even ADM, there are you can give data sets on a Cauchy slice. This is a very famous result of crucial and delay, which can describe multi black hole solutions configurations. So you can have separated black holes far away from Kerr black holes far away from each other, such that the metric at large distance is Minkowski. And so can you give Cauchy data on a slice which solves to give you this solution where you have far away separated black holes? You know that.
Still tell the ADM data.
Yes.
Still,
You provide a data. At least it's a theorem, so I don't know how much practical. I mean, it is more function analytic proof, but you can. This is not inconsistent with that. It is not an unrealistic statement that we could have a Cauchy data which would give us multiple black holes which are scattering.
so maybe another way to ask my question: can you still tell the difference between the velocity of the first black hole and the velocity of the second black hole and the velocity of the third black hole just by looking at asymptotic data?
Just by looking at classical asymptotic data, that I would not think so, because they provide local data which depends on individual masses and then glue it.
That is why the question about ADM, because
Okay, that's a good point. Yeah. So the ADM from infinity we only see total,
yes.
total mass or total momentum. We can't distinguish.
But also you made a comment about how you're seeing only the mass and spin, which is in some sense tied to ADM.
Oh, sorry. No, I appreciate your point. Okay. No. That's why I said it is related to Noether theorem. So,
Yeah,
so
you see no other hair.
yes.
But now if you have more than one black hole,
Yeah. So here our setup. No, that's an excellent point, Sachin. So what I'm saying right now is the following. So this is for a single Kerr black hole. What we have done, right? Now we are saying we take. So each Kerr black hole we are mimicking as a point particle with some spin and p. And now we are saying that okay, we have many Kerr black holes which are scattering off each other. So the first.
at the moment they may not even, they may even be moving away from each other.
They can be anything, yeah. So then the first order correction that happens is that the mass and the spin become time dependent because they are influenced by each other, right? Other particles, right? Because spin can change, the Kerr black hole can start slowing down because it's emitting energy, right? Or they can, like, the two masses can fuse into each other, you know. So that's the first order correction which is taken into account by putting explicit dependence on in both the sigma and the p on explicit sigma dependence on the spin and the momentum. Yeah. Is there something more nuanced you have in mind? I mean, you would agree this is a zeroth order. Yeah. No. I think I am seeing your point. I don't think I have a very good answer to your question, but you would agree this is like a first heuristic correction we expect when we have more than one black holes with interactions, say gravitational or other interactions. No, you are not happy. You are.
No, that's fine. As you know, I have a lot of trouble with boosting, especially in the quantum field.
That we will. Yeah. No, you are right. But this is.
But that's fine.
Yeah, this.
The theory, the question then becomes about ADM. But we can discuss this.
Yeah. Okay. So I hope, please, if there is any question, no question about this, then this is now our setup, that we have these particles with mass, spin, and in general any other multiple movement. So if you have a Kerr black hole, everything is fixed by, for a one Kerr black hole, as Sachin mentioned also, as momentum and spin. But if you have a general neutron star, it can have other multiple moments that we parameterize as some Ti. I can go from 1 to infinity in general. They are just some data. Yeah.
So the mass of the scalar particle will correspond to the mass of the black hole.
Exactly.
And what will be the proxy for the angular momentum?
Spin, the ring radius of the Kerr black hole, the spin of the Kerr black hole.
So far as the scalar particle is concerned?
No. So we have the scalar particle is some intrinsic. For classically, spin is some. It's just some extra data on a particle. It's like extra multiple moment, not just the mass, right? It's independent degree of freedom than mass. Yeah. So I don't know. Arka can say more. There is some way to model this as also a rigid body, not just a point particle, right? And then think of the spin coming from some. But we are just. Is that correct statement that we are just thinking of this point particle with independent parameters, mass and spin? And so.
Sorry, but then why couldn't I have considered a higher spin particle?
No, you.
A high spin field of a certain mass.
Yes.
And the spin of that field corresponds to the spin of the black hole.
So I think, yeah, I mean, what you are asking is very relevant. That so here, okay, so maybe I say a little bit about this. So the philosophy here is that, okay, to start to view collision of black holes or neutron stars from large distance, we are first modeling them as we would do in effective field theory as point particle with some extra data. And what you see, these extra multiple movements, you could think of them as coming from some higher spin fields, related to the higher spin fields. Now, for Kerr black hole is strange in the sense that it is not only a spin one object. It has infinitely many higher spins, but they are all fixed by one parameter. So this is a statement that in particle physics literature is now famous, that Kerr black hole is a infinite spin particle which consistently couples to gravity, which intuitively seems counterintuitive because we know that particle with spin higher than 5/2 don't couple to gravity. But in this Kerr black hole, you take the spin to, in some sense, you take a point particle, it's take its spin to infinity, mass to infinity, and keep the ratio constant, and its coupling with gravitational field is consistent to leading order. So Kerr has infinite, from your perspective, Kerr has infinitely many higher spins, but they are all fixed by one parameter.
5/2 statement that you just now made is true only for, is also true for massive particles?
Yes.
So you can't consistently couple it.
Yes. But then you see that motivated by the Justin Wien's result, people ask that if I take this T mu nu, can I consistently couple it with H mu nu? I mean, just a linearized graviton. And that can be done because this is conserved, as Justin Wien showed. So that means this is a mysterious object in that sense, that it is an object which has, in some sense, infinitely many spins. All of them are fixed by one parameter, but it seems to consistently couple, at least to leading order, with gravity. So this is this work of Utin and Nima and others that try to model Kerr black hole as a point particle, even in quantum field theory, but that proposal has run into now, as we would expect, this difficulty of considering coupling comes when you really look at these amplitudes more carefully. No. Yeah. No, I don't think so.
You can scatter gravitons with an infinite number of higher spin exchanges.
But it's infinite tower, right? So this statement is about a fixed spin object, right? So it's finite spin fixed. String theory bypasses it in an interesting way because it is the tower never truncates. Yeah, here it's not at all. Nothing is. It's all just classical. It's just it's our classical spin. But, it's related to the spin of the Kerr black hole in GR, directly related. Exactly. I mean, at this point we have no fundamental description for it. It is, we just importing it from the metric of a curved black hole.
The other comment, I don't know whether it's how relevant.
Yeah.
Sigma when what you have written, epsilon sigma b, that's just the Pauli velocity, right?
Yeah. Sorry, no, sigma is the spin. I mean the
Angular momentum.
yeah, is the spin.
If you were to write the angular momentum,
Yeah.
then it will be just take Pauli. So
Yeah.
sigma if you wrote J.
Exactly. That's what it. Yes. Yes.
Presumably in the rest frame,
No. The sigma is independent of. So even in the rest frame, sigma is not.
so if you go to the rest frame, then J is equal to sigma.
It's just sigma. Yeah. Okay. Now we now that we have our setup complete, I'm going to now tell you how we. Let me now go first give you the result and then we try to give. How much time? Yeah. Okay. So maybe can I take 2 minutes exactly?
Yes.
Okay.
Just to why we are truncating, because there is the head of the AI IBM division is coming in to discuss very informally with us about the future of AI in India. So anybody who wants to participate in the discussion, please stay on.
So let me just write the result and we prove it next time. Is that fine?
Yeah.
So in D greater than 4 dimensions, strictly greater than 4 dimensions, this is what we will prove, that in any theory of gravity, so it can be Einstein-Hilbert or it can have other higher derivative, higher powers of Riemann in its action, etc. The following is true. So remember, this was the radiative metric that we defined. Times plus one more term, which is the following. So I will write, sorry, if you can't see, please ask, I will write it above. I will explain, I am introducing one more vector that I will explain in a minute. Maybe. Where this J, so we will see all this in detail, okay, the lack of time I am just writing the final result, is the orbital angular momentum of the ith particle plus the spin. Plus, okay, now let me explain in 1 minute. So what have I done? What we will prove is that if I compute this radiative metric in omega, and if I look at it in the, if I am interested in the soft radiation, that is low frequency radiation, then it turns out that the first term we will find, which will scale as 1 by omega, and it's completely fixed only by the initial and final momenta of our objects, nothing else in any theory of gravity. If I go to one next order in omega, so this is 1 by omega order, the next order in omega is of course omega to the 0, and that term is again completely independent of the details of the theory or what is happening in this region, and it's completely fixed by the total angular momentum, which is orbital plus spin, and the linear momenta of the particles. And of course then the next term will be order omega term, and these terms start depending more and more on details of the theory. So these two terms are truly universal, like you take these objects which are allowed in your theory of gravity, scatter them, doesn't matter what the details of the scattering are, you wait for the final objects to come out, And if you are interested in the low frequency radiation, this is an analytic formula for the first two terms in the low frequency expansion. So this is the statement. This is called first event shape, sometimes called memory in 4 dimensions. So it's an interesting observable because it's truly universal. Like it has no dependence on details of your scattering or anything. A second event shape. Okay. Anyway, we will discuss it more next time. But this is the result that we will prove. Spend at least half an hour trying to see the proof of this thing. So maybe I can stop here for today. Except this one will not be universal, only the first term will be universal.
And that you can get by just modeling it
As a kick. But here, so in the same way, this term is actually trivial. It is this term whose universality is slightly more non-trivial.
So when you say trivial, what you mean is you can model it as a kick.
But just because, like Jackson has done it in his book, that for electromagnetism, in chapter 13, he says that if you just want to look at radiation at leading order, you model it as a kick and you get this result. Oh, yeah. Yes. For electrodynamics, Jackson also has it. Classical, just classical. Okay, but yeah, so we will prove this next time. We should stop, right?